Assalamu alaikum and welcome to lecture number 29. In this lecture we are going to talk about the Fourier we continue the previous topic of the properties of the Fourier. A similar problem you have encountered while we were doing the properties of LTI system, and we have to find the inverse. We said if the two systems are inverse of each other, in that case their impulse responses will be equal to impulse, right? So on the next slide we have provided the same problem. So here is the same problem you have encountered, and because there we were doing the convolution, right? And you understand that in time domain convolution results into multiplication in the frequency domain. So that's quite straightforward there. So let's see how we use the properties to find the inverse system. So to solve this problem, first we need the impulse response. So what is the impulse response of this system? So you understand finding impulse response is quite straightforward from the given input output relationships. And in this particular case we can say we define the impulse response as output of the system when input is impulse. So that means y of n equals to this. So to find the impulse response, we straight away, because we say impulse response is the output of the system, right? So we replace output by impulse response, and then we say when input is impulse. So we replace input by impulse. So xn is replaced by impulse of n, and a times x of n minus 1, it will be replaced by impulse of n minus 1. So that means we have the impulse response equals to impulse and its scaled and shifted version, right? So let's write the relationship for that. So the let we say that the causal inverse system has impulse response h inverse of n, right? And by exploiting the property that if two systems are inverse of each other, then their impulse responses, the convolution of their impulse responses will result into impulse. So this is equal to impulse, right? And remember, this problem you have already done, but now we'll exploit the properties of the Fourier, right? So we take the Fourier transform of both sides, right? Take the Fourier transform of both sides. So H inverse will have Fourier transform H inverse j omega. In fact, we replace this omega by capital 1 because we have used this notation, right? I hope you understand. And because convolution in frequency domain becomes multiplication, so we generally do not put any sign, so that means it is multiplication, right? So this will be h of j omega, and this is equal to, and you understand Fourier transform of impulse is 1, right? Now to find the because we need to find the H inverse, right? So to find H inverse, because H j omega is multiplied here, so if I shift it to the other side, it will be divided. So that means H inverse of j omega equals to 1 over H j omega. Okay. So we can write that H inverse of j omega equals to 1 over H of j omega. Okay, now what is h of j omega? So because h of n equals to, so h of n equals to impulse of n plus a times impulse of n minus 1. So by applying the Fourier transform formula, we get h of j omega equals to, right, I just write the equation here so that it becomes clear to you, summation, and we say n running from minus infinity up to infinity, and this is impulse of n e power minus j omega n, and plus summation and running from minus infinity up to infinity, right, a times impulse of n minus 1, and this is equal to n multiplied by minus j omega and n, right? So you understand for the first part that impulse remains 0 from minus infinity up to infinity except at the point where its argument is 0. So its argument will be 0 when n equals to 0. So if I replace n with 0, so we get e power 0, and e power 0 equals to 1, and this is also 1, so I get 1 plus, again for here we have impulse, so impulse is 0 from minus infinity up to infinity except at a point where its argument is 0. Now its argument will be 0 where? When n equals to 1, right? So when n equals to 1, at that point this will be 1, right? This is equal to 1 when n equals to 1. And what will be this one? This will be, if I replace 1 here, so it will be e power minus j omega. So a is scaling, so a comes here, and we have e power minus j omega. So that's the frequency response of the original system. And remember, we need to find the frequency response and the impulse response of the inverse system. So what will be the frequency response of the inverse system? By just putting its value, we get the inverse frequency response of the inverse system. So that means we have, this is something to 1 over a sorry, not a, in fact it's 1 1 plus a e power minus j omega, right? And this we can also write that 1 over 1 minus, and if I write minus a here, e power j minus omega, and this, right? So using the summation formula, if you recall, if you have some summation like using this equation, we can find the inverse Fourier of this, right? So remember that this is basically beta, right? So this is beta, so that means this result will be only valid when minus a times e power minus j omega times e power minus j omega is less than 1, right? So so that means this will result into summation and running from so that means this is your beta. So if we compare this one, so that means this is equal to summation k running from 0 up to infinity beta power k. So let me replace here. So let me just, because this is your beta, right? So let me write some small. So okay, this is your beta. Okay, so the summation and this running from my right, and then we have minus j omega, and we can take like their beta power k. So here variable of summation is n, right? So this can be expanded into summation k n running from 0 up to infinity, and I can write this n on individual terms. So I can write a power n into e power minus j omega n, right? Now, so for example, we have h inverse of n. Okay, so h inverse of j omega, right? So the Fourier will be for this. For example, we have the h inverse of n in time domain. So to convert in frequency domain, we'll use the formula, right? That's the Fourier formula for summation from minus infinity up to infinity. Then we have h of n, right? And e power minus j omega n, right? So that's what the situation is depicted here. Okay, so you have h of j omega and h inverse of j omega, and this is equal to summation n running from 0 up to infinity, right? So if you compare these two equations, you can say that basically h of n equals to this. You understand? And because we are not summing it from minus infinity, so we are actually summing it from 0. So that means the hn, if I write right, so hn will be equal to basically h inverse of n basically equals to minus a power n times step function u of n. So this will be the impulse response of the inverse system, right? So quite straightforward, because in time domain we have convolution, so in frequency domain we have the multiplication. So if we take the multiplication of Fourier transform of both sides, so h inverse of h inverse of n convolve with h of n equals to impulse of n. So we take the convolution of the Fourier transform of both sides. So this will result, convolution will result into multiplication. So that means h inverse of j omega multiplied by h j omega will be equal to 1, because the Fourier transform of impulse is 1, and then by putting the value of the impulse response here we get this one, and then that's quite straightforward, because this thing, if you compare with the standard summation formula, you have used this formula so many times, so I hope you will remember it, and if you didn't, then memorize it. Okay, so in the formula we have minus here, so that means if I write it like this, so it's quite equal to this formula. So that means we have 1 over 1 minus this whole will be your beta, right? So this means it's equal to basically this thing, right? So this, right? So I just wrote here and running from, because our variable of summation was n, so I say okay, and running from 0 up to infinity, and we just write the beta value here, and then I split it, right? So we get this thing, and if I compare this with the standard Fourier transform formula, then I find this is basically my h of n, and because the integration summation starts from 0, so that means we have a power n into u of n. So that is my impulse response for this system, right? This is the frequency response of the inverse system, right? So from frequency response we can easily find the impulse response. Okay, so let's consider another example. Here we are given the input signal and output signal, and we have to find the impulse response, right? So if we use time domain, so it's quite difficult, right? Because in time domain we have y of t equals to x of t convolved with h of t. So it's quite difficult to find the h of t. From this relationship you need to know the deconvolution and complex processes, right? Difficult processes, right? So if we just go for the frequency domain, that's quite straightforward. Because convolution in time domain basically equals to multiplication in frequency domain, right? So the Fourier transform of y of t will be h of t. So the Fourier transform of this will be y of j omega equals to x of j omega times h of j omega. Okay, so how to find x of j omega? So that's straightforward, right? Should I do it, or I just, okay, that's integration minus this to this, and it will be e power minus 2t u of t and e power minus j omega t dt, right? So because we have u of t here, so that means limit cannot be minus infinity, because u of t will be 0, so the product will result into 0 from minus infinity up to 0. So we can just, okay, similarly the two terms are multiplied, right? These two are multiplied, bases are same, so power will be added. So that means I can write it here, minus j omega t, and skip this, right? So if I take t common, in fact minus t common, so I am left with if I take minus t common, then I have this will become plus, right? Because I am taking minus t common, so this is your t and this becomes plus. So you have this. Again, now the integration of this will be e power, right here is minus, so minus t 2 plus j omega and divided by minus 2 plus j omega, and the limit of integration are 0 to infinity, right? So you understand, to integrate you put the first limit or upper limit and find, and then minus the lower limit. So upper limit if I put here, so this t, this whole thing becomes infinity. In fact minus is there, so it will be e power minus infinity, and e power minus infinity is basically 0. If you put the lower limit, which is 0, so it is e power 0 is basically 1, so 0 minus 1, you get this thing, and you get minus 2 plus j omega, right? So this minus cancels with this minus, so you get something like 1 over, right? So this is the Fourier transform for x of t. Similarly, Fourier transform for y of t will be 1 over 1 plus j omega. Okay. Now to find h of j omega, x of j omega is multiplied, so it's like if I bring it this way, this side, it will become divided. So that means I can write that h of j omega equals to y of j omega divided by x of j omega. So I hope using the same equation or similar procedure you can find the y of j omega, right? So y of j omega, if I just straight away write, is y of j omega equals to y of j omega equals to 1 over 1 plus j omega, right? So if I put the value of here, so it will be 1 over 1 plus, okay, I made a mistake, it's x of j omega, right? Not h of j omega. So this is x of j omega, so it will be 1 over j omega, right? And divided by x of j omega, right? So x of j omega equals to this. So for division I can reciprocate it, so that means division can be written as, because x of j omega is divided it, so I will just inverse it, right? So it's actually 1 over 2 plus j omega, so it can be written as 2 plus j omega, because double division is involved, right? So that means I can write it like this: 2 plus j omega divided by 1 plus j omega, right? So to skip the partial fractions, I can just write it in a simpler form. So I can also write it like this: 2, so 2 is basically 1 plus 1. Okay, so that means I can write 1 over 1 plus j omega plus 1 plus j omega divided by 1 plus j omega. Okay, because I have 1 plus j omega, so I can write it 1 over 1 plus j omega plus 1 plus j omega over, right? So these two stands cancel. Okay, so I get 1 over 1 plus j omega and plus 1. So this is my h of j omega, right? So because Fourier is basically linear operation, right? So you can say, okay, to find the inverse of it, so inverse of it can be, okay, I write it by h of t. Okay, so h of t means I can apply Fourier inverse to this term, right? And I can apply Fourier inverse to this term. So what is the, this is basically Fourier transform of what? This Fourier transform of this, right? 1 over 1 plus j omega is basically Fourier transform of this. So that means if I take inverse of it, I should get e power minus t u of t. Okay, plus what is the Fourier transform of 1? 1 is Fourier transform of what? So quite, if you recall, so this is basically impulse. If you take the Fourier transform of impulse, you get 1. So that means inverse of the Fourier will also be, right, because they are reciprocal of each other, right? So if I take Fourier transform of impulse of t, I get 1. So that means the Fourier inverse of 1 will be impulse of t. So this is the impulse response of this system. So you can see that how straightforward it is to find it using the Fourier transform. So next property we consider here is the time integration, right? So if x of t has a continuous time Fourier transform equals to x of j omega, then if we integrate this one with respect to time from minus infinity up to t, it will result into 1 over j omega, x of j omega plus x of plus pi times x of 0 impulse of times impulse, right? So to derive this expression, let's consider we have y of t such that y of t equals to integration of the above signal minus infinity up to t, and we have x of tau and d tau, right? So if I integrate both sides with respect to time, right? Differentiate, right? With respect to time. So we get d upon dt of y of t, and this will be equal to x of t, right? Now if I take Fourier transform, right? Fourier transform of both sides. So if I take Fourier transform of both sides, you understand multiplication, differentiation in time domain corresponds to multiplication by j omega. So that means we have j omega times y of omega, which is Fourier transform of y of t, and this is equal to x of j omega, right? So that means we can say y of j omega basically equals to one over j omega j omega times x of j omega. But at y equals to omega equals to 0, right? So if I put omega equals to 0, you understand it will be 1 over 0, so it will be indeterminate, right? So that means this is valid for those signals with the 0 time average value, or which has 0 DC value. So that means for those signals which have 0 DC value, that means x of j omega equals to 0, so it will result into 0 when omega is 0, right? So it's valid only for the, this notation is valid only for the signal which have 0 DC value, right? So for non-DC for signals which have non-zero DC value or average value, we can modify the expression. So we can modify the expression, and we can say we write that y of j omega equals to 1 over j omega x of j omega plus pi times the x of 0, right, and impulse, right? So we add this term for those signals that have non-zero DC value. So this is what exactly is here. So that means y of j omega is basically what? Y of j omega is the time derivative, right? Y of j omega equals to integration of the x of t. So that means integration from minus infinity up to t x of tau equals to 1 over j omega, right? So I hope you understand the relationship. Y of t, we just denote it for the integration, that we say y of t equals to integration of this is your y of t, right? And whatever you get here, this is your, this whole is your y of j omega, right? And you know that why we add this extra term, or why we add this extra term. Okay, so let's consider an example. For example, we have input signal, the u of t. So what will be the integration Fourier transform of u of t, right? So we cannot straight away calculate it because it is not absolutely integrable, because it's 1 from 0 up to infinity. So if you take the integration, so it will result into some it will result into infinite. So in ordinary way we cannot find the Fourier transform of the step function because this is condition, right? So to find the Fourier transform of the step function, we use the relation, right? Because we need to find the Fourier transform of step function, and you know step function equals to, right, integration minus infinity up to t, and that is impulse of tau deta, right? So that is the relationship between step function and impulse function. You have done this in the first part of the course, right? I hope you also understand what is the relationship between discrete time impulse, discrete time step and impulse. So you understand there we use running sum, so it will be summation minus infinity up to n, right? So by using this expression, right, this is your x of t is basically your impulse of tau. So if I take the Fourier transform, so what is the Fourier transform of impulse of tau, right? So I just write 1 over j omega, and the Fourier transform of the step is 1, right? So that means should I just write 1, right? Multiply by 1 and plus pi. So what is the value of x of 0, right? So that is, okay, just I write here x of 0 and times impulse in frequency domain, right? So what is the value of x of 0? Because you know that in case of step impulse function, right, the Fourier transform of impulse, right, what is it? It is equal to 1. It is constant. So that means if I say this x of j omega, so x of j omega 0 equals to 1, x of j omega 1 equals to 1, so it's 1 all the way. So I can just replace it by 1. So that means x of j omega, x of this is also 1, so it is just simplifies to impulse of omega. So this is the expression, or this is the value of the Fourier transform of the step function, right? I can also remove this 1 because 1 multiplied by 1 basically equals to 1. So I can just remove this one also. So what you are left with, this is 1 over j omega plus impulse of, all right, so this is the Fourier transform of the step function. Parseval's relationship states that energy or power in time domain representation of a signal is equal to the energy or power in the frequency domain representation. So we know that energy in time domain equals to x of t absolute square dt, and integration is from minus infinity up to infinity. So this is same as finding energy in the Fourier domain, and this is equal to 1 over 2 pi integration x of j omega square dw, right? So let's consider an example. For example, we are given a signal in frequency domain as described here, and we need to find the energy of this signal. So we know that, so one way is that we transform the signal into time domain and using this equation to find the energy. But we can also find the energy in frequency domain as given by the Parseval's relation, and we know that E equals to 1 over 2 pi integration from minus infinity up to infinity, and x of j omega absolute square df w. So let's find the energy of this signal. Now 1 over 2 pi is the scaling factor, so let's take it out and we just write. Now if we look at the signal, it's a piecewise, so from minus 1 up to 0.5 it has value equal to pi. So we say okay, pi, and the value is from minus 1 up to 0.5 minus 0.5, right? And square of this into dw plus integration. So from minus 0.5 up to 0.5 its value is pi by 2, so minus 0.5 up to 0.5 we have pi by 2 square dw, right? And plus integration from 0.5 up to 1, again it's pi, so 0.5 up to 1, again it's pi square dw. So this is equal to, so on simplification you understand that we put the upper limit minus lower limit, so pi square, upper limit is minus 0.5 and lower is minus 1, so minus 1 means plus 1. Again here we have upper limit which is equal to 0.5 minus lower limit, so lower limit also minus, so that means minus minus plus 0.5 plus 0.5 plus, from here we have pi square, and the limits are minus 0.5 to 1, so that means upper limit is 1, lower limit is 0.5, so 1 minus 0.5 will result into 0.5. So this is 0.5 for the first one. We take the pi square as common, so on simplification we get 1, this will be 1 plus 1 by 4 is basically 5 by 4, and 5 by 4 multiplied by pi by 2 is 5 by 8 into pi, right? So this is the case when we take, I think this is square root of pi, right? So this is for the case of pi, okay, because I have taken it pi, so for pi we have this one. So you can try for the case when you have the same signal and you have square root of pi, and this is square root of pi by 2. So you can go and do it by yourself for the case when its value is square root of pi and square root of pi by 2. So remember that 2 is out of the square root. So this is about the Parseval's relation. We have observed symmetry, in fact consistent symmetry between the time and the frequency domain representations of the signal, right? And you understand, for example, a rectangular pulse in time domain corresponds to sinc function, or similarly a rectangular pulse in frequency domain corresponds to a sinc function in time domain. Also uh, pulse in time domain corresponds to a constant signal in frequency domain, and similarly a pulse in frequency domain, if we go to the time domain, we see that it is everywhere, that is a DC signal or a constant signal. Similarly, convolution in time domain corresponds to multiplication in frequency domain, or multiplication in time domain corresponds to the convolution in frequency domain. These symmetries are a result of the symmetry in the definition of time and frequency domain representations. For example, we can write the representation here. We know that x of j omega equals to integration from minus infinity up to infinity x of t into e power minus j omega t df t, and similarly x of t equals to 1 by 2 pi integration from minus infinity up to infinity, and we have x of j omega and e power j omega t df t. So the difference between x of t and x of j omega is basically the scaling factor. You see here we have 1 by 2 pi in case of x of t, and there is no 1 by 2 pi, so that's just the scaling factor. And here we have positive minus j omega t, that is omega is negative here, and here omega is positive. So the sign difference we can say. So we have just the difference of scaling and sign of omega in these two expressions or definitions for the time and frequency domain signals. So we can say that x of t has continuous time Fourier transform x of j omega, and if I replace the omega by t and scaling factor of 2 pi, so that means x of jt, you understand I have replaced omega with t here, so now x of j omega instead of x of j omega, now we have x of jt, so its Fourier transform will be 2 pi x of minus omega. So we have changed the role of time and frequency, right? So this equation we say that, so x of jt means that we have changed the variable here from frequency into time, right? While here we say that we have replaced time with minus omega, right? So that means we have replaced t by the reflected frequency minus omega. So using this property we can solve many numerical problems which seems otherwise very difficult. So let's consider some more examples here. So if you look at here, this is a pulse in time domain, right? So if you have a pulse in time domain, then its Fourier transform will be sinc function. You understand, this is a sinc function. We have done this example or similar examples, right? Similarly, if you have a sinc function in time domain, then in frequency domain we will have a pulse, right, as defined here.